In this video, we're going to talk about how the cell membrane is selective in that it is only permeable to very specific compounds. So what I have here is our simplified diagram of a cell membrane, and I'm going to say that this is very zoomed in, more zoomed in than we're used to. So even when we're drawing the phospholipids next to each other, we have to remember that there is a little bit of space between them, albeit a very small amount of space, but there's still space. And the phospholipid heads of the membrane are not locked together like we think they would be. Rather, they have some wave-like motion that makes them look almost like the surface of the ocean. So some things are able to pass through these membranes. And sometimes things get stuck for a little while and then they pass through the membrane. But we need to talk about which things those are. And when we talk about this, again, we have to remember how small we are getting here. So we're talking in the nanometer range. And a nanometer is 1/1,000,000th of a meter. So the width of the cell membrane is 8 nanometers at maximum. Let's just write in to remind ourselves that the phospholipid heads are going to be charged. They're also going to be polar. And this makes them hydrophilic, meaning they like water. On the other hand, these tails are going to be uncharged. Remember, because they only have carbon and hydrogen bonds. That also makes them nonpolar, because the electrons are being shared evenly. And they are hydrophobic, meaning that they fear water. They do not like to be near water. And I'm also going to write in that we have that -2 charge from the phosphate group here as well. So now let's look at permeability with a charged ion. These are going to be quite large. So you'll see I'll draw in a chlorine ion with its negative charge, and I'll make it very large. This negative charge repels the negative charge that we have on our phosphate group. So it's very unlikely this chloride ion is going to be able to go through the cell membrane by itself. The other problem, as you can probably guess by the size of this chlorine ion, is that the chlorine is so big that it is not going to make it through the membrane. So you may be asking, what if we have a positively charged ion? So let's take the example of a potassium ion, K+. Whereas chlorine gets repelled by the -2 charge from our phosphate group, potassium is more likely to just get stuck to that -2 charge. And again, potassium is way too big to fit in between the heads of our phospholipids. So, in summary here, charged ions are not permeable. And that's again because of their charge, but also because of their size. So now we're going to look at large and uncharged polar molecules. These are also going to be highly unlikely to pass through the cell membrane. Again, they're way too big. The only way I could think about it happening would be if there are so many that they literally shove one of their large and uncharged but polar friends through that membrane, causing those phospholipid heads to move to the side, like I'm representing with these dotted lines here. And maybe, just maybe, you'll get enough force and enough pressure to shove one of those large and uncharged but polar molecules through that membrane. Again, this is highly unlikely. Another problem here is that if it's polar, there are going to be dipoles. And yes, dipoles aren't full charges like our chlorine and our potassium ions, but they're still partial charges. And so when we have the same partial charge, so negative to negative or positive to positive, for example, they still will repel. So now we're going to look at the small and uncharged polar molecules. So nothing has changed here except for the size. And yes, we still have that issue with our dipoles. Those areas of slight charge, they are going to repel. Not as much as our chlorine ion, but you're still going to have some resistance here. But maybe if enough force is put behind it, maybe we can get this through the membrane. Highly unlikely, but again, I'm imagining that we have a lot of these on one side of the membrane and they just force their friend through the membrane. So now we're going to look at small, uncharged, and nonpolar molecules. You can ignore the frowny face in the nonpolar tails. But here is our small, uncharged, nonpolar molecule. And here's the big difference. Not only is it small now, but it's also nonpolar. And the tails are going to like that a lot more. These molecules will have a very easy time passing through the cell membrane because they're not charged, and because they're nonpolar, they also don't have dipoles. So there's really no repelling going on here. So as an overview of membrane permeability, charged ions are the worst because the charge on the ion is going to either repel from the membrane itself because of that phosphate group, or it's going to be stuck to the outside of the membrane. Large molecules that are polar are also not very helpful. Because of their size, it's going to be very hard for them to get through the cell membrane. And it doesn't help that they're polar. While being polar is not as bad as being charged, you still have dipoles, and those dipoles are areas of slight charge, which can still be repelled by the dipoles on the membrane. If we get smaller, we have more luck. But small molecules that are polar are still less likely to be able to go through the membrane compared to small molecules that are nonpolar.